Right here, we'll look at question 3 in section 13.6. We're asked to compute the directional derivatives d of f in the I direction and d of f in the j direction for a function z equals f of xy. And then it asks, what do you notice? Okay, well, let's go ahead and just write out what these things are saying from that result we derived in computing directional derivatives in terms of the gradient. Okay, so this would be the gradient of f dotted with our unit vector, which happens to just be the basis vector I. Okay, so now this is what? It's the vector partial f partial x, comma partial f partial y, and we're going to dot that with the vector I, which in this angle bracket notation, right? It's just standard basis vector. It goes one unit in the positive x direction, and the y component there is 0. So taking this dot product, notice all I'm going to get is partial f partial x. All right, so now if you think back to what we said when we motivated in the intro video the directional derivative, we said, well, this thing is just going to compute for us the slope of our surface in the direction of our unit vector. Well, here, if I'm moving in the direction of the basis vector I, what I'm really doing there, right, is I'm moving in the positive x direction. And so going back now to 13.4, that was precisely our definition of this partial derivative of f with respect to x. This thing was the slope of our surface in the positive x direction. So this makes perfectly good sense. And of course, for the derivative of f in the j direction, right, it's really the same thing, just now looking at this unit vector as 0, 1 now, right? So this is just going to give us the partial derivative of f with respect to y, right? Because we're now moving in the positive y direction, and so this derivative is just telling us the slope of our surface in that direction. Okay, so that makes perfect sense. So the last thing I'm going to say here, right, is in a more general direction. Like let's say I move in the direction of a unit vector u, where that again has magnitude 1, so it's a unit vector. Then the derivative of f in this direction is, well, the gradient dotted u, which is this computation here, and we can write that out as this, okay? So notice, right, the components of our unit vector, the u1 and the u2, are weighting the partial derivatives, partial f partial x and partial f partial y. So the general directional derivative is really a weighted sum of these two partial derivatives. And in the extreme cases, that's what we have up here, right? If I go just in the pure x direction, so there's no movement in the y direction, I'm just going to get partial f partial x, right? u1 would be 1, u2 would be 0. And here's the other extreme where it's just motion just purely in the y direction. There's no x movement. Okay, and so more generally we would get this combination. Okay, now for those of you that taken linear algebra, you could also call this a linear combination of these quantities, which are the partial derivatives of f with respect to x and y. All right, cool. Well, that's going to do it for this problem.